Voyager 1 was not alone. It had a twin. 16 days earlier, on August 20th, 1977, humanity had launched another spacecraft on an even longer journey. A 1,615-pound probe placed on a slower, more ambitious path, one designed to visit not 2 planets, but 4. Voyager 2 was sent to exploit something rare, a planetary alignment that only occurs once every 176 years. Today, nearly 5 decades later, it drifts through a darkness so absolute that the Sun is just another star. Currently over 13 billion miles from Earth, with no fuel to change course, no way to turn around, no chance of rescue, and just like its twin, Voyager 2 is dying. But the story doesn't end when its power fails. That's merely the prologue to its true odyssey. AI is replacing jobs faster than ever, but the people who learn it are the ones getting ahead. The problem? Most people want to learn AI but don't know where to start. New tools launch every week, and scattered tutorials can make you feel overwhelmed. Introducing Outskill, an AI learning platform helping millions of learners worldwide understand and apply AI in practical ways. Their 2-day live AI mastermind condenses insights from over 100 practitioners from companies like NVIDIA and Microsoft into a powerful 16-hour experience. They are hosting a live workshop this weekend from 10 a.m. Eastern Standard Time to 7 p.m. Eastern Standard Time. You'll learn how to build AI agents, automate workflows, connect tools like Google Sheets and Notion, and start using AI to save hours every week. Click the link below to grab your free seat before spots fill up. Huge thanks to Outskill for supporting this video. Voyager 2's original mission was straightforward: fly past Jupiter, fly past Saturn, study their atmospheres, moons, and rings, send the data home. That was supposed to be the end of it. But the engineers in NASA's Jet Propulsion Laboratory had designed the trajectory to exploit that rare alignment: Jupiter, Saturn, Uranus, and Neptune arranged in a sweeping arc on the same side of the Sun. If the timing was right, each planet's gravity could fling Voyager 2 toward the next one without burning a single drop of extra fuel. It's like throwing a ball at a moving train and having the train kick it forward faster than you ever could have thrown it yourself. The physics worked, and so did the spacecraft. Voyager 2 reached Jupiter in July of 1979, flying within 350,000 miles of the planet's cloud tops. It captured images of the Great Red Spot, a storm the size of 3 Earths. It confirmed active volcanoes on the moon Io, eruptions of sulfur and molten rock on a world that should have been frozen solid. At Saturn in August 1981, it revealed that what looked like smooth ring bands from Earth were actually thousands of individual ringlets braided and sculpted by the gravity of tiny shepherd moons. Every visit raised more questions than it answered, and every visit flung Voyager 2 faster toward the next one. In January 1986, Voyager 2 became the first and only spacecraft to visit Uranus. The planet was tilted on its side, rolling through its orbit like a ball instead of spinning like a top. Its magnetic field was off-center, tilted at a bizarre angle. Its moon Miranda looked like it had been smashed apart and reassembled by gravity into a patchwork of mismatched terrain. Then came Neptune in August 1989. Voyager 2 passed within 3,100 miles of Neptune's cloud tops, closer than any encounter on the entire journey. It discovered winds screaming at over 1,200 miles per hour, the fastest measured in the solar system. It found geysers on the frozen moon Triton, plumes of nitrogen erupting from a surface colder than minus 390 degrees Fahrenheit. No spacecraft has returned to either of these worlds since. Voyager 2 remains the only machine that has ever seen Uranus and Neptune up close, and it had a few hours at each. After Neptune, there were no more targets, no more gravity assists. The spacecraft was slung south and outward from the plane of the planets, accelerating away from the Sun. It has been on that trajectory ever since, just momentum and silence. Enjoy deep, fact-checked space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. So, what keeps Voyager 2 alive? three small devices called radioisotope thermoelectric generators, powered by the radioactive decay of plutonium-238. When Voyager 2 launched, these generators produced about 470 watts of electrical power. That's less than what a typical microwave oven uses. But it was enough to run 10 scientific instruments, a radio transmitter, heaters, and the computers that control it all. The problem is that plutonium-238 has a half-life of roughly 88 years. The power supply drops about 4 watts per year. That may not sound like much, but on a spacecraft where every watt counts, 4 watts is the difference between keeping an instrument alive and shutting it off forever. The engineers at JPL have been making these decisions for decades. One by one, cameras, spectrometers, and heaters went dark. By 2024, only a handful of instruments remained active. In early 2025, NASA turned off 2 more science instruments across the twin Voyagers to buy a few more years. The engineers believe they can stretch operations into the early 2030s. But at some point, the power will drop below the minimum needed to operate the radio transmitter. When that happens, Voyager 2 will send its last signal to Earth, a whisper of data traveling at the speed of light, taking over 19 hours to cross the gap, and then nothing, permanent and total. Even now, communicating with Voyager 2 is extraordinary. The spacecraft transmits with a radio power of about 22 watts, roughly the same as a refrigerator light bulb. By the time that signal reaches Earth, it carries less energy than the impact of a falling snowflake. Yet, NASA's 230-foot deep space network dishes can still hear it. For now. When the power finally runs out, Voyager 2 will simply stop talking. The instruments will go cold. The antenna will point wherever it was last aimed, and the spacecraft will continue unchanged. Here's where the story becomes something else entirely, because Voyager 2 is not going to stop moving, ever. It has achieved solar escape velocity, meaning the sun's gravity can never pull it back. It is leaving the solar system permanently, but most people believe Voyager 2 has already escaped the solar system. This is technically false. Yes, in November 2018, Voyager 2 crossed the heliopause, the boundary where solar wind ends and interstellar medium begins. This made global headlines, but crossing the heliopause doesn't mean leaving the solar system. The true boundary is the Oort Cloud, a massive spherical shell of trillions of icy objects bound by the sun's gravity. The inner edge may begin at around 1,000 astronomical units from the sun. The outer edge may extend to 100,000 astronomical units, nearly 2 light years. Voyager 2 is currently at about 143 astronomical units, traveling at roughly 34,000 miles per hour. It will take roughly 300 years just to reach the Oort Cloud's inner edge, and it could take another 30,000 years to pass through entirely. Think about that scale. For context, 30,000 years ago, humans were painting animals on cave walls. We had not yet invented agriculture. The entirety of recorded human civilization fits inside the time it will take Voyager 2 to cross this one region of our own solar system. And during all of that time, Voyager 2 will be completely dead. Just a piece of metal and silicon and gold tumbling silently through a cloud of frozen debris that no human eye has ever seen. If Voyager 2 survives the Oort Cloud, it will eventually approach another star. In roughly 42,000 years, around the year 42,025 AD, Voyager 2 will pass within about 1.7 light years of a small red dwarf called Ross 248 in the constellation Andromeda. But 1.7 light years is not close. Light itself would take nearly 2 years to cross that gap. Voyager 2 will not orbit Ross 248. It will not be captured. It will drift past unnoticed, a speck of metal in an ocean of nothing, completely indifferent to whatever happened to its creators 40 millennia earlier. And if Voyager 2 remains undisturbed for another 296,000 years beyond that, it is projected to pass within about 4.3 light years of Sirius, the brightest star in our night sky. It will not stop. It will simply continue on a 250,000-year drift through the galactic neighborhood. At this timescale, continents on Earth will have shifted dramatically. Ice ages will have come and gone multiple times. Mountain ranges will have eroded completely. Entire species will have evolved and gone extinct. Yet, Voyager's course remains precisely as calculated, following the exact trajectory determined by slide rules and early computers in the 1970s. But here's what makes this story more than just a physics problem. Bolted to the side of Voyager 2 is a golden record, a 12-inch gold-plated copper disc designed to be playable for up to 1 billion years. It was the idea of Carl Sagan, the astronomer who understood that space exploration is not just about data, it is about meaning. Sagan assembled a small team, and together they encoded 116 images of Earth. Photographs of mountains, cities, oceans, a woman nursing a child. They included sounds, thunder, wind, birdsong, whale calls, a mother's first words to her newborn, laughter. They recorded greetings in 55 languages, from Akkadian spoken in ancient Sumer 6,000 years ago, to a message from Carl's 6-year-old son Nick, who said simply, "Hello from the children of planet Earth." They added 90 minutes of music: Bach, Beethoven, Stravinsky, Javanese gamelan, Chuck Berry, Blind Willie Johnson. And then there was Anne Druyan, the creative director of the project. During the creation of the record, she and Carl Sagan fell in love. 2 days after they first confessed their feelings, Druyan went to a hospital in New York where her brainwaves and heartbeat were recorded and compressed onto the disc. She later described thinking about the wonder of falling in love, the vastness of the universe, the improbability of being alive at all. Her heartbeat is on that record right now, 13 billion miles from where it was first felt. The record's cover is etched with instructions for playing it, a pulsar map to triangulate Earth's position, and a sample of uranium-238 whose decay rate allows the finder to calculate how long it has been traveling. The record will almost certainly outlast everything else. Voyager 2's electronics will die in the 2030s. Its structure will be slowly eroded by cosmic dust over millions of years. But the golden record is projected to remain legible for 1 billion years. Long after every trace of our current civilization has crumbled, long after the continents have shifted beyond recognition, that record will still be out there carrying the sound of thunder and a child's voice, and Beethoven, and the heartbeat of a woman who is thinking about love. No one will hear it. The spaces between stars are simply too vast, and the spacecraft is simply too tiny. Carl Sagan knew this, but he also said that the act of launching it, the act of throwing a bottle into the cosmic ocean, said something hopeful about the species that did it. We built Voyager 2 in the 1970s. Its onboard computer processes about 8,000 instructions per second. A modern smartphone handles more than 14 billion. It was never designed for immortality. It was designed to photograph Jupiter and Saturn and send the pictures home. Everything after that has been a gift. Sometime in the next decade, an engineer at the Jet Propulsion Laboratory will send a final command, the signal that will take over 19 hours to arrive. There may be a reply or there may be silence, and then the most distant active ambassador of the human species will become the most distant relic. It will keep moving. It will carry with it the sound of wind on Earth, greetings in languages, some of which have already gone extinct, music written by people who have been dead for centuries, and the heartbeat of a woman who fell in love during the making of something that was never supposed to last this long. The universe does not care about Voyager 2. The void will not mourn it. The stars it passes will not notice it. But we built it. We aimed it at the edge of everything we knew, and we strapped to its side a golden record that says, in every way we could think of, we were here, we were alive, and we wanted you to know. Voyager 2's twin is out there too, traveling even faster, even farther into the void. But where exactly is Voyager 1 headed? What will be its final destination before the stars swallow it forever? Watch what is the last destination Voyager 1 will ever reach to find out. Huge thanks to Outskill for supporting this video.